This is the Mathematics Education Podcast from mathedpodcast.com. Welcome to the Math Ed Podcast. My name is Sam Otten from the University of Missouri, and I am joined today by Ryota Matsuura, who's an Associate Professor of Mathematics at St Olaf College in Minnesota. Ryota, thanks so much for being here.
Oh, thanks for having me.
We're going to talk about a few topics, starting with his article in Mathematics Teaching in the Middle School, which is called The Search for Hidden Structure, and that was written with Sarah Sword and Tatiana Finkelstein. And later on, we'll also be talking about the Budapest Semesters in Mathematics Education, which Ryota helps to direct. But before we get there, Ryota, I always start back at the beginning of your academic career, and I was wondering where you did your graduate studies and who you worked with there.
So I was at Boston University, but let me backtrack a little bit. Before I went to graduate school, I was a high school teacher in the Boston area for a few years, which I absolutely loved the job, but I also loved doing math. Mm-hmm. And so I went to graduate school in mathematics, and I did number theory there, and my advisor is David Rorlick, who's just one of the best teachers I've had. And I went to BU because while I was getting my MAT, which I also got at BU, I went through their Promise for Teachers program, which is this wonderful summer immersion experience for both in-service and pre-service teachers, where you just experience mathematics as mathematicians would. I think that's the motto of the program, and that really kind of ties along with my article as well. Mm-hmm. Anyhow, so going to BU to do mathematics was somewhat of a natural choice. And when I was at grad school, I sort of led a double life, if you will. I was studying for my PhD in number theory, but I could never let go of that part of working with teachers. And so I did a lot of work with local teachers. I did a study group with middle school teachers. I was a judge at math fairs at local high school. And so my advisor, who was very understanding of kind of that life I led, and I finished in relatively decent time. Mm-hmm. So, and then after I graduated, I kind of had two paths. I could have gone the straight math route or more of the math education route, working with teachers. And so that's the route I took. And I did a postdoc at the School of Education at Boston University, where Suzanne Chapin was my postdoc mentor. And so that's how I ended up in the math education world.
So at St. Olaf College, how are your responsibilities balanced? So you're in a math department, right? But do you still keep, obviously, a lot of your energy spent in the math education side of things?
Right. It's, in some sense, an ideal job for me in the sense that, I teach math classes like my math colleagues, so linear algebra, abstract algebra, these courses that I really enjoy teaching and work with the math majors. But we also have our math education program for pre-service teachers. And so these are math majors who want to become secondary teachers of math. And so I direct a small but vibrant program, as I like to think of. Mm-hmm. And I work with about 5-6 students per year to help them become secondary teachers. And so it's really a nice balance of my dual passion of doing math and teaching math, but also working with the math education program we have.
Mm-hmm. So your article in volume 23 of Mathematics Teaching in the Middle School is a blend of some mathematical ideas, but then written for a teacher audience, and it's called The Search for Hidden Structure, and it's really digging into mathematical structure and how to bring that forward with students, and you connect to the Common Core State Standards with Practice 7, which is look for and use mathematical structure. But I was wondering if you could just tell us, how do you think about mathematical structure? How would you define it, or how have you found a useful way to operationalize that for teachers? And then what do you think are the benefits to learners for really focusing on that mathematical structure? Why is it beneficial in an education setting rather than just as mathematical ideas in the abstract?
Right. So, I think of mathematical structure, it's a pretty loaded phrase, and I think it can mean a lot of things, but in some sense it's what people look for when they do mathematics, right? So mathematics isn't just about doing separate computations and getting answers to all these different problems that have nothing to do with each other, but it's about relationships and connections, I think. And NCTM's Principles to Actions does a pretty good job of describing it. I think it says something like relationships among ideas or relationships among mathematical ideas. And so that's what I think of when I think about structure, that there are these patterns in these problems that students can look for and generalize and make conjectures about what's going on and give some insight and explanation to what's happening under the hood. And so, even simple examples like, well, if you take a pair of odd numbers, you get an even integer. And sure, 5 plus 7 is 12, and 7 plus 9 is 16, and that can happen for about 10 different examples, but there is something underneath. It happens for any pair of odd numbers, and why does that happen, and can you explain what's going on? And so that's a kind of a simple example, but I think it says a lot about what mathematics is about, that it's more than just finding what 7 plus 9 is. It's thinking about, well, what's happening here? And so that was the theme of our paper.
And it seems like some of the benefits would be it's a more authentic experience for students because they're actually thinking in ways that mathematically we would hope that they would think. And another benefit seems like the why. So you mentioned you can actually see what's going on under the hood, and that seems like that would help learners, right? Because it's probably going to stay with them longer, it's going to make more sense, they can build upon it if they actually see what's going on underneath.
Yeah, absolutely. I mean, I think, I always say that rarely, or if ever, things happen by chance in mathematics. If it's a good problem or it's a well-constructed lesson, there hopefully is some sort of a structure that's lurking underneath, and part of the fun, at least I think of it as fun, and hopefully our students think of it as fun, is solving the puzzle and figuring out what's going on. And I think it does, I mean, you said, absolutely, students, I believe, remember things more. But also I think it makes it more meaningful to the kids that math is a useful subject, absolutely, no doubt about it, and there are lots of applications to real life. But there's also this component that, when you're doing something authentic, it becomes meaningful, and you feel that sense of ownership and empowerment of figuring things out. And, I always compare it to some other subjects like history, which I don't think history is just about memorizing a bunch of events and dates. There's some patterns that happen in our history that you want to make sense of. And likewise for music, you're not just playing a bunch of notes that are strung together. There's some structure underneath. And I think it's the same for mathematics, and hopefully that's what we can convey to our students.
So in the article in MTMS, you talk about 3 specific practices that are kind of at the lesson level, and you talk about these as ways of emphasizing the mathematical structure and trying to make those accessible to students. So can you first of all just kind of talk us through those 3 practices and maybe give us a couple examples so we can wrap our heads around them?
Sure. So the first one is using, we call it using routine exercises to scaffold the lesson. And so, if there is some idea that we want students to find out, then we would kind of take them through the calculations, if you will. And these are really routine exercises. They're not necessarily challenging, but we ask the exercises, repeatedly. Common Core's Standards for Mathematical Practice, the 8th practice, is about repeated reasoning. That if you do these calculations repeatedly, not necessarily as practice problems of something that they've already learned, but really as a means of discovering a certain concept, that students see patterns arising in these calculations, and hopefully that can lead to generalizations. And so the first principle that we talked about in the article is these routine exercises, again, not huge, big problems. In the paper, we talked about finding the distance between 2 points whose y values are the same. And so really focusing on the x values and thinking about their difference. And initially, we had the kids plot the points actually on the grid. And so some of them were counting boxes. Some of them, if their point was on one side of the y-axis and another side of the y-axis, they were just adding the distance from the y-axis, for example. And so the kids were having different approaches, but eventually it led to them coming up with a general approach that works in all situations. And so that was our idea of doing some repeated reasoning.
And the arithmetic was never that challenging, but the point was to really see the structure of what are we actually finding? Can we think of this as a distance? Can we think of it as a length? Can we think of it as an arithmetic value? So making the connection about, hey, this is all actually rooted in an underlying structure.
Yeah, and that's a good point. We didn't want the calculations to be so challenging that they really lose the sight of what they were doing. And so that's a very good point, that we kept the numbers fairly simple enough for the kids who are in that class, and really they can go through them fairly quickly to get the rhythm of the calculation.
Mm-hmm. And this is interesting to kind of lead an article with, like, hey, use routine exercises. And I've actually had an experience like this as well, where I wrote a chapter in the NCTM book on the Common Core mathematical practices with Kessler, Felton, and Bieta and myself. But I was the lead writer on chapter 8, which is on practice 8, about repeated reasoning. And I kind of had the same feeling of like, are people going to just look at the surface of my chapter and say, hey, he's calling for routine exercises, which seems like a kind of low-level sort of thing. But the point is that you are thinking and you're making connections and noticing things while you're doing the routine exercises. That's the key. And it's the same thing you're saying in your article. You don't do the routine exercises just to get them done like busy work. You do the routine exercises because they become something you can look at, think about, talk about, and then realize, oh, I see what's going on underneath.
Right. And I think that's where, the teaching part comes into in-class teaching of the teacher. So we can prepare all these problems for the kids to work on, but if you just let them go, some students will really reflect on what they're doing, but, there are plenty of students who will just kind of go through it, go through the motions, check, I'm done. And it really does take a skilled teacher who, one of our authors, Tatiana Finkelstein, she's the classroom teacher who taught this lesson. She would kind of stop and ask the kids, okay, so what's going on here? What did you do? Can you talk about it with your table group? Things like that. And so it really does take a skilled teacher to bring out some of that reflective thinking in the students as well.
Yeah, which leads us right to the second practice then, right?
Right. So the second one is about language. And so you go through this experience, you go through this, all these examples and calculations. And so then the next step is, well, can you articulate the observations that you're making using precise mathematical language? And so that was a really challenging part for the students, that they can do some of these calculations, but can you articulate it in a way that applies to all situations? And so the language that we used is from a paper by Coco, Goldenberg, and Mark, where they said that the students, they can do the calculations, but the shoehorning the insights that those kids had, shoehorning those insights into precise language, that's somewhat of a challenge for the students. And so we were hoping to give them enough time and space to be able to do that without the teacher just, okay, let's bring it together and go over it and let me articulate it for you. Our goal in this lesson was to give students the opportunity to do some of that articulation.
Yeah. And what was some of the things that they tried to express, but that, maybe got more precise as they were talking about it or talking through it?
Right. And so going back to that example of having points along the same y value. Some of the kids would say things like, well, they're at the same height, and that was already fairly precise. The points are in the same row. I think that was one of the quotes that students said, same height, and then they started using language like, well, you can have a horizontal line between those 2 points, and then eventually getting to saying that they have the same y coordinate. And so the more precise you get, you actually tease out some of the mathematical ideas that, okay, so you start off saying that points are in the same row. Well, there's not much really you can do about it mathematically. It does describe what they see. But then by the time they get to saying that the pair of points have the same y coordinate, now you can talk about, okay, so what can we do? That if they have the same y coordinate, maybe that's not the one that matters. Which coordinates are you actually using to find the distance between those 2 points? And then the students realizing, oh, okay, so we should be focusing on the x coordinates. And so being able to say it more and more precisely, it sure helps to communicate, but I think it also helps to clarify one's thinking. And when you have to generate a formula, for example, in some way, formula is also a very precise articulation of one's thinking. And so to get there, it doesn't happen immediately, that it takes some time and some steps to fine-tune your language until you can say it so precisely that, in some sense, the formula just comes out of that process.
Yeah, and then the formula has a lot of meaning because they realize, oh, this encapsulates everything we've been talking about and seeing.
Exactly. Yeah. And I think that we hoped was what was happening is by providing a lot of those experiences, is that the generalization that they made at the end is just a summary of a lot of the experiences that they've already had. And it's nothing new, really. It's just a precise statement of what they've been doing all along.
And so the third practice is providing a storyline, which actually probably connects with what you're just saying here about, hey, we've been doing something and it led somewhere. And that's this idea of a storyline. Can you say more about that?
Right. And so, these students, they had studied the Pythagorean theorem, and they knew how to plot points on the coordinate plane, and they knew that the notion of distance is something they've known for a long time. But to really connect them all together, that was what we thought of as a mathematical storyline, and how those pieces fit together to come up with a coherent whole, if you will. And so, it's one thing to come up with a distance formula. It's another thing to really understand where each piece comes from and making sense of how they fit together. And so that's the kind of storyline that we wanted students to form. And so, we started off by having them actually draw out some of those triangles, right triangles. We didn't tell them they were right triangles, but they can see it clearly when they plot the points on the coordinate plane, and then they would find individual legs and then ask them to find the hypotenuse. And then, again, this is repeated reasoning. Again, we would have them do that calculation several times, and they realize, oh, I see what's happening here. And then some of the student work that we have in the paper really demonstrate that they've understood how the algebra of finding distances and the geometry of the Pythagorean theorem fit together nicely.
And so we can tell this is all eventually leading to not only seeing those connections, but then having the distance formula, and hopefully they would have meaning for the distance formula. But I thought it was interesting in the article that the lesson does not actually end with the distance formula, and there's a line in the article that says, the teacher actually made the decision to withhold the distance formula, and she thought that they would be ready for it soon, but they weren't quite ready for it yet. And to me, that just makes me think about this big issue in math education about when do we present the formula. Some books or some teachers might actually start with the formula and say, here's the distance formula. Now let's try to unpack the structure of it and try to wrap our heads around it. Whereas this article talks more about giving these experiences, building the language and the storyline, and then when the moment is right, the formula will be an encapsulation like after the fact. I wonder if you just wanted to comment on that debate that's kind of, ongoing in mathematics education about the order of things.
Right. And so, we think of it, the authors and I, we think of it as providing experience before formality. And so we're definitely in the camp of the formula coming as a culmination of the experiences that we provide the students. And so, when I work with my pre-service teachers, I often talk about it as a flipped model, not the flipped model that's out there where you do a videotape of a classroom and then have the students watch it, but flipping the typical presentation in textbooks where you see the formulas up front, followed by the explanation of the formulas and exercises. We like to take the model of kind of going the other way, where we provide these repeated calculations to the students. Start with the exercises, not the practice problems of something that they've already learned, but like I said earlier, these exercises that lead to a particular concept, and then they see some patterns and they try to articulate it very precisely, and then hopefully when they're ready, generate the formula at the end, more of a summary than a starting point. And so that's the pedagogical model that we took in this lesson, and something that I try to model in my own teaching and try to get my future teachers to think about it that way as well, as a possible way of teaching.
I'm speaking with Ryota Matsuura from St Olaf College, and we've been talking about his article on math teaching in the middle school, but another thing that Ryota is very involved in the math education community is the Budapest Semesters in Mathematics Education, which is a study abroad experience that's specifically for mathematics education, where future teachers can actually go over to Hungary and get some mathematics education preparation there and some experiences, and then come back to the United States with a lot of excitement and passion and new ideas about teaching mathematics education. So first of all, I was wondering if you could just add to that description of BSME, and also just let us know how BSME got started.
Sure. So BSME started with BSM, Budapest Semesters in Mathematics, which is a very well-known study abroad program in pure mathematics that's been going on for, I'd say, almost 35 years for undergraduates. And one of the hallmark for BSM is this Hungarian approach to learning mathematics, which is very inquiry-based, problem-solving based, learning by doing, kind of like really goes along with the article that we talked about. And I'd say about 5 years ago or so, the people who are running BSM started wondering, well, this pedagogical approach work for undergrad math students? Well, why can't it work for future teachers and people who are interested in teaching, and really dig into not just the mathematical side, but the pedagogical side of BSM? As you know, Hungary has produced a lot of great mathematicians and math educators. I mean, Polya obviously comes to mind, Ryotas, and just a lot of mathematicians have come out of Hungary and math educators.
Yeah.
And so BSME started, our first semester was the fall of 2015, as a way to introducing this Hungarian approach to learning and doing mathematics, which is based on, again, problem solving, inquiry, discovery, communication, all those good things about doing math in Hungary, and trying to bring that to an American audience.
Yeah, so I got to actually go visit the program. I was lucky enough to go over for a few days and get to meet the students and the instructors, and got to go to some schools. And I was really impressed with the problem-solving approach, because it's basically a chance to just get into a different culture of math education. Here in the U.S., a lot of times we talk about, we have to fight against the inertia of this tradition in the U.S. of like top down, the teacher just tells you what to do, and then you have to do it over and over again, and everybody's brain starts to slowly shut down. But it's nice to go to this other culture where it's like, oh no, the students come and they are ready to dig into problems. And getting to talk to instructors who said, like, yeah, we have these 3 problem strings that we're working on, and the students get to push each of them forward, and then we know that it's going to eventually culminate in these big mathematical ideas, but it's like a string of problems that are all leading there. Was really cool to hear about and to see. And it was also fun to see the students who are in these math classes. I talked to one group of students who spent most of a class period stuck on this problem, and I asked them as they were leaving, like, hey, what do you think about math? Do you like math? And I wasn't sure what they were going to say, because they literally were stuck for quite a while. And they all said, oh, we love math. And even this student who had not even unlocked the problem by the end of the period, she was just smiling and said, I love math. And this was, quote unquote, like the low algebra class, to kind of use that kind of rough language. So to find a group of students in a, quote unquote, low class, to see them stuck for most of a period, and then for them to just immediately say, I love mathematics, was something that I've never seen quite that way in a United States classroom.
Yeah, it's definitely part of their culture, it seems like. I've been working with Hungarians for the past few years. It's been a blast. But it seems to be that their culture of doing math in this particular way of, like solving puzzles, just problem solving as a way of learning math is really definitely ingrained into the way they learn in Hungary. Part of our mission is to bring that to an American audience of future teachers.
Mm-hmm. So what would be the actual ways that somebody might be able to participate in the program?
Right. So we have a semester program both in the fall and spring. And so mostly undergrads, although we've had some master's students as well. Everything is on our website, which is bsmeducation.com. But starting this summer, in summer of 2018, we also have a summer program that's open to, well, really everyone, in-service teachers as well. I mean, obviously, in-service teachers, it would be a challenge for them to spend a whole semester during the fall or spring. But that's why we've mostly had undergrads and master's students. But in the summer, we're very open and welcoming of the in-service perspective as well. And so we're looking forward to the summer program, which, again, will start this coming summer in 2018.
Mm-hmm. And one thing that I thought was pretty cool was the undergraduates, when they go there in the fall or the spring, they have these math education instructors who are I think to a person, pretty amazing. But those instructors are actually also teachers in the classroom, and so the undergrads can go do their field experiences with their methods instructors, which to me is just an amazing opportunity, because here in the U.S., and most of the schools I'm familiar with in the U.S., the methods instructors are kind of university-based teacher educators, but then the students go to the schools and then they have host teachers who are teachers in the classrooms, and there's not always strong alignment. Sometimes there's good alignment, but it's not guaranteed. In the BSME program, it's actually the same person. So you can go to the college class and talk about these ideas of math education, and then you can actually go and see that same person with real students and see how it works.
Yeah, I think our instructors are our best asset. They are, every one of them is a practicing secondary teacher. And so, as you said, our participants, BSME participants, do get to visit those instructors' classrooms, as well as several different classrooms all over Budapest. And there's also an opportunity to teach their own lesson that they developed to actual students in Hungary. At a bilingual school, so everything is done in English, including the instruction and observation. Many of the classes are in Hungarian, but there's live translation, so you can really listen to what's happening live in English. You know, there's also the academic side to the program, but one of the things that we hear from past participants is just the experience of living in this different culture, different city for 4 months, which is really a transformative experience for our participants. And Budapest is just one of the most exciting, beautiful cities I've been in, and so that's a huge plus as well.
Yeah, and it was great. I wish I could have been there longer, but it was a great opportunity to go and experience that. And again, it's bsmeducation.com where they can go for more details. Did I get that right?
Correct.
Well, Ryota, thanks so much for talking about that work that you're doing. And I have one final question that I ask all the guests. This is to imagine if you were not in mathematics or math education, if you didn't have this perfect balance of the two fields at St Olaf College, but what could you imagine doing as an alternative career entirely?
I like to make things, so carpenter, perhaps?
Okay.
When I do math, I do think of it as making ideas, but I also like to make physical things as well, like origami folding, for example. And so I don't think I can make money with origami folding, so maybe carpenter is something I like to try if I had a chance.
Yeah. Do you imagine like big kind of projects, or do you imagine more like skilled, like very small crafts kind of things, or small furniture sort of things?
I can go either way, but maybe going beyond something like the IKEA furniture that I built, something a little more substantial than that.
Yeah. Well, that's great. Well, Ryota, it's been a pleasure speaking with you, and I hope you have a great winter break.
Thank you so much for having me. This was a blast.